Hi, I'm Alex. I'm the inventor of volumetric solar architecture. Volumetric solar is a revolutionary 3D photovoltaic product that generates electricity from dawn till dusk, just like trees. I'm excited to share this innovation with you. So back in 2012, MIT created a study called Solar Energy in Three Dimensions, and they combined a number of different fields: architecture, material sciences, with calculations and also prototype testing. And what they found was that cubic structures can create more energy than flat photovoltaic structures over the hours of the day and different seasons and different testing conditions. So this report was really interesting back in 2012 when it came out, but 13 years has passed and not much has happened in the field of 3D photovoltaics since. But this is the closest science to vertical solar energy collection. In their example, they used flat single-sided sheets to create prototypes, and they wired these in parallel, and then they measured and calculated the different expected power generations. So why is solar energy 3D on Earth? It's 3D because of the tilt of the Earth, and Earth is rotating every day, every 24 hours, and then it rotates around the sun every 365 and a quarter days. When the sun sends energy to Earth, it is 2D in space, but once it gets in Earth's atmosphere, it turns into 3D. So the clouds and anything in the atmosphere can basically bend and shift the light from 2D into 3D. And then when it strikes different objects at the ground level, it can reflect. And so the reflection and the bending of light in Earth's atmosphere makes sunlight 3D. One of the biggest differences between the amount of energy is the location where Earth is around the sun. So that's what gives us the seasons. Because the Earth has a tilted axis of 23 degrees, 23 and a half, that means that we have winter with shorter days and longer nights, and summer with longer days and shorter nights in the northern hemisphere. So the angle of the sunlight is what determines how much energy is reaching any point on the surface. So the winter hours are very different than the summer hours of sunlight. And so what we need to do with solar energy on Earth is to capture the maximum hours of sunlight, whether it's 6 in the winter, as shown on the left, or it's 16 in the summer. And so the angle is really important. It comes down to geometry, and the sun always rises in the east at a low angle, and it always sets in the west at a low angle. But depending on the season, it may sometimes be overhead, but it may sometimes be low on the horizon, depending on where you are on the Earth's latitude and what season you're in. So this is really key to understand just how much solar energy reaches the Earth and how important angles are in collecting this across the most amount of time. So right now, solar energy collection, solar power is pretty much done in 2D, and I call this 2D photovoltaics. And that happens because people are pointing all the solar panels up at the sky facing typically to the south. If you're in the northern hemisphere, you point it to your panels to the south. If you're in the southern hemisphere, you point it to the north. But what happens is the middle of the day becomes the highest solar energy output, and that happens typically between 10 a.m. and 3 p.m. So you get about 5 hours a day of maximum 2D solar energy. But what we saw in the previous image was that the amount of sunlight in a day can actually be a lot longer. So we're only gathering a few hours of the daily solar power that's available from sunrise to sunset. And so the other problem is that the way that people use electricity is the highest in the morning and the evening, especially the evening. So there's a gap between the time when solar is over-generated, middle of the day, and when it's used in the evening peak demand period between 4 and 8 p.m. typically. And so that supply gap is a real challenge for the utilities, and they have to find ways to either ramp up production from fossil fuels power plants or have battery storage or something to make up that gap. But it makes it really difficult for adding solar to the grid, because during the middle of the day, the price and the demand of solar energy is really low. So in some places, it's even negative that the power produced by solar is over capacity in the middle of the day. So what we need to do is to be able to shift more solar energy across the full number of hours, and especially in that evening peak, to be able to make up for that gap. And that's what volumetric solar can do, is it can increase the hours per day. So now when we generate in that peak demand window, that value of electricity can be multiple times the value of the electricity with midday solar. So a single hour of evening electricity that's solar can be worth 5 or even 10 times more the electricity than the middle of the day. So generating in that window of time is the most important thing to meet the mismatch here. The other big factor is seasons between snow seasons in northern latitudes, and the snow is really a big factor. Like huge losses with snow, based on that study on the left there with the Sandia National Laboratory. They're talking about 100% losses over months, and then maintaining the panels and clearing the snow and ice off of it. We're going to see in the next slide that the snow is a huge problem because it really reduces the current output of the entire string of connected panels. So every panel has to be cleared to get your maximum production back. And why does this happen? It's because all of the solar panels right now are wired in series, and that's just like old Christmas lights or holiday lights. So what's happening is the current across a string of series connected devices is always shared. And so whatever the lowest current is of the string is what they're all going to share. It's like a pipe with water, and whatever the lowest water flow is the output of the whole string. And that's just how solar panels are wired today. They're all wired in series. And so with the current being the least, you have to basically face them all in the exact same direction. And conventionally, that has been tilting them up to the sky or pointing them all in the same south or north configuration. And so if any one of those modules is pointed the wrong way, it's going to have a different current than the rest of its neighbors, and it's going to cause the entire connected string to reduce its power. And so that is why there are all these flat arrays. But because it's flat, it makes it 2D, and you can only generate about 5 hours of peak sun. And if you want more, you have to use trackers. So you can put flat solar panels in with one side facing up. You can put tilted solar panels in that are fixed. You can also put trackers that are single axis trackers. So that means they can basically pivot front to back. Or you can put dual axis trackers, which have front to back motion and east to west motion. So you're trying to follow the sun across the sky when it rises in the east and sets in the west. But you can imagine that doing that for a string that's connected with lots of solar panels is really expensive, because you have to have mechanical motors and timing and all that sort of stuff figured out, and you need a lot of land to fit all that onto. So that's what's happening right now in conventional solar. Wired in series, you've got single axis or dual axis trackers if you want more hours of the day beyond that 5 hour window. So to solve this problem, we really have to understand DC electricity basics. And the example on the top there is how every solar panel is wired today, which is series first. So those 4 solar bifacial modules are wired in series. When you tilt them up, they create a shadow behind them. And that shadow makes it so that the backside light can't really do much. You don't get much of a direct or bounced light from the backside. So they're basically shading the back of those panels. But most important to understand is how DC power works in solar panels. So the power of every panel is the panel's voltage times its current. And voltage is really easy to generate, especially with bifacial panels that have two sides. So even a little bit of sunlight will get you a good voltage. And typically that means about 40 volts per module, per panel, for these utility scale panels. So you get to 40 volts DC, and they're all pretty constant at 40 volts. But what really changes the power, and the most important part, is the current. So that's the amps. And your power is your voltage times your amps. And as we looked at, for series wired modules, you always get the minimum current of any connected module in the string. So the way volumetric solar works, the foundational core is that you wire the modules in parallel first, so they all share the same voltage, probably about 40 volts DC if you're using utility grade bifacial panels. And then the currents are added together. So it doesn't matter which way the modules are facing, because they're all getting enough light to have the same voltage. And then whether the modules have 1 amp, 2 amps, 10 amps, 20 amps, those amps are all added together to the plus and the minus output. And then you can decide from there what you want to do next. Do you want to connect another volumetric solar unit in series and add its voltage together, or do you want to connect another one in parallel and add its currents together? But this parallel first wiring enables the modules to not face the same direction, and so that makes them stackable. You can stack them up. So just like you're stacking up leaves on a tree, you can keep increasing the volume by adding more modules in parallel. And the example on the left there, you got 4 bifacial modules in parallel. The middle one, you've got 8, and the one on the right, you've got 12. So we've got a fixed 2D area at the bottom, about 4 meters square, but we're adding more and more power vertically, and we're adding that through more and more amps. So our voltage stays the same, and we're adding higher and higher amps using the third dimension, vertical dimension. So just like a tree is growing upwards, or plants grow upwards, that fundamentally lets you capture more power and energy using the same area, which is totally different than the series wired panels where they need more and more area. So the taller you build these structures, the more power and energy you can generate. And putting that all together, volumetric solar architecture combines bifacial modules with parallel first wiring. You don't need any sun trackers because you're not following the sun. The sun is just moving through the sky because Earth is rotating on its axis and around in the seasons. And then reflection boost is another topic I'll talk about, but you can reflect the light from below, from behind. Any one of those modules has more sunlight reflected on it, it will increase the current of the combined circuit because they're wired in parallel. And doing that with a minimum area and maximum hours is what volumetric solar architecture achieves. So this is a totally new way of doing solar that doesn't require expensive trackers and doesn't have this relationship with more area. We can get more energy through volume by building upwards, and there's no limit. The taller you build these structures, the more current you can add together in parallel, and that current can be used for all sorts of charging applications, and I'll talk about that in a little bit. So what I've been working on as the inventor is creating this global IP portfolio of copyrights, industrial designs, utility patent applications to standardize the architecture. And then I built and engineered prototypes that you can see here. And the nice thing about these is that they're all compatible with off-the-shelf modules. So you don't have to have some custom module made. You can use any bifacial module, and I'll go into how these are mounted, but with 4 posts, essentially, you can get these up off the ground. And so off the ground, you can get reflected energy from below, in the middle, and then up from above. So also testing this in the seasons was critical, that I could see in the summertime, we've got maximum hours from the morning to the sunset. And then the winter time that we can shed snow with that vertical glass on the front and the back side. So A lot of testing went into this product to build this in a really economical way to get solar power installed in 3 dimensions. So why do plants grow up? The answer is to collect sunlight in 3D, I think. So the diagram on the left is what I did as a rendering in SketchUp with shadow simulation to show, and then the version on the right is what I was able to build. It's a volumetric solar 4x1 unit, 4 bifacial modules, and then extending that, we can add another set of 4. So we got a volumetric solar 4x2 with 8 bifacial modules, and so these 8 modules are connected together in parallel. A couple other features I was able to figure out and standardize: parallel wiring connectors. So it's easy to connect the plus and minus outputs of each module together using these 4-to-1 connectors. So they are MC4 connectors, plug and play DC, 4 plus, 4 minus, and then you have a plus and a minus output of each. You can install that all on the inside and it remains hidden. You can't even see it from the outside. So the other part is the solar clamps. So being able to adjust the height and use these end clamps to go up and down through these aluminum rails. You can adjust the height as you need to across different seasons and conditions, especially snow. And then various options for freestanding legs. So you can connect directly into the earth. You can use base plates. You can attach to existing structures, and it's really customizable in terms of what types of methods you want to attach. So whether it's roof, ground, sides of buildings, mountaintops, deserts, anywhere you can find a way to attach these structures in a rugged way. And what I found in that testing was these aluminum frames of the bifacial modules are actually rated for hurricanes. They're super strong aluminum ratings. So the other thing here is plug and play DC batteries. So combining those outputs into parallel, you get a plus and a minus. And so you can connect those right into the back of these portable generator units, and they've got batteries inside. So this is basically like a DC coupled battery charging system. The DC solar is low voltage and higher current from volumetric solar. It goes right into the battery, plug and play DC. You don't need an electrician. It's under 100 volts. It's plug and play. So this really lets you take your power plant charging infrastructure and your storage anywhere. And the output of these units has AC, so it has an inverter built in. And you can also connect it to the grid, so you can back up your solar power with grid power or generator if you need to. But it allows for rapid deployment. You don't have to change the ground or install all this different pilings and stuff like that. It's quick to install and pop up, and you can connect in battery storage. And so it doesn't really matter what time of the day it is. You'll be charging that battery from dawn till dusk. The other thing you can do, which I think a lot of mechanical engineers and other kind of scientists and engineers miss, is taking renewable energy and turning it directly into heat. So the output of that battery, you can connect in resistive heating, and you can heat air, water, boil water. You can heat sand, thermal batteries. But the idea is that you can also take DC electricity directly from these structures and connect them into resistive heating elements to create clean heat anywhere, right? So if you think of a hot water tank or other kind of boiling solutions, why not integrate high density solar energy into that? And now you can. So volumetric solar for me was a solution set for microgrid. So this diagram shows volumetric solar at the top left. It doesn't have a cost of energy. The sun is your fuel. It doesn't make any emissions. It's going to be used as a battery charging solution. So you can connect it directly to a DC battery that is shown there in the middle. And then you can also connect in the grid for backup. So if your battery's low and it's nighttime or there isn't solar energy, you can recharge that battery from the grid. And you can also connect in existing generators like diesel gen sets or wind turbines and provide another source of charging your battery. So we're taking electrons from the cleanest source, which is solar, potentially the grid, depending on how clean or dirty the grid is. A lot of grids are burning fossil fuels to keep the lights on and to power things. And then we also have, on-demand site backup for generators, especially for off-grid, remote locations, construction sites. You're using a lot of diesel generators to make electricity on site. Problem is with burning fossil fuels, you're losing about 75% of that energy through combustion and heat. It's not an efficient way to make electricity. Plus, you've got the emissions factor. But by integrating this together in a microgrid, you can then add more battery ion storage. So if you want a longer storage time, it's easy to add more batteries in parallel, add more volumetric solar generators in parallel, and you can essentially increase your generator and your storage time. Then the output of the battery, you take an inverter and you turn into AC. And that's how you can integrate it back into the power grid that you have right now. So alternating current works well for a lot of situations, but you always need an electrician for AC power. If you're changing a panel or doing wiring changes, 120 volts and above, you need a way to integrate that quickly. So this microgrid approach lets you add solar generation and tiered backup into existing buildings, and those buildings can be housing networks and computers, EV chargers, heat pumps, hot water tanks. The AC electricity doesn't know where it's going, but it can just be seamlessly integrated into all sorts of downstream applications. So the biggest factor to understand is that with renewable energy, curtailment is kind of the worst case. So if you're not taking free solar energy and either charging a battery or powering a computer or charging a vehicle or powering a heat pump or turning it into hot water, if you're just doing nothing with it, then that's the worst use of solar energy. And so your efficiency isn't so much how much can you save, but it's how much solar energy can you put to use to solve all these downstream problems. And that's what we can do with volumetric solar as a part of a microgrid solution. So business model, I've invented this product. It's an architectural product for bifacial modules. Anyone can license this directly from the volumetric.solar website. Globally, if you want to install your own, make your own, sell your own, that's available today. So you can go and buy a license and do that commercially as a company or individual. I've got plans for engineering, procurement, and construction. That's the field that I come from. I know that field well, and it's really quite a challenge with getting these big projects done quickly. So my idea with volumetric solar is to provide EPC services to do these DC fast charging networks. So it's quick to pop these up. A volumetric solar forest is a DC plug-and-play solution with DC batteries, and then we can integrate that clean energy into all sorts of applications. The ones that we can displace fossil fuels will also generate carbon credits. So charging a vehicle or replacing diesel fuel or creating heat, those are all able to be verified carbon credits that can be bought and sold to offset emissions elsewhere. So far, the traction we've got has been pretty good for this new product. It's a very new type of architecture. Takes people some time to wrap their heads around it. Everybody thinks solar power has to be flat for some reason. But this is novel IP, so I'm the IP holder of it. And the web store is online for sales. We just had our first commercial installation March 2025. That's the example on the left there. And that's a volumetric solar tree. So it's got a galvanized steel post and platform that fits right onto a standard lighting base. And we took that 4x1 unit and installed it on top of the platform, so it's up high. And those panels are wired in parallel so that they produce a plus and a minus. And that battery unit that you saw a couple slides back is what's sitting inside of a sign and powering some LED lights. So It's a DC plug-and-play solution, no AC grid required, and it just recharges the battery morning, noon, all the way into the evening, sunrise to sunset. The main thing to also know is that when the sun rises in the morning and sets in the evening, the angle is really low. So you're unable to get that energy from pointing the panels up. You have to have vertical faces to collect that energy at the start of the day and the end of the day. So the next big application we're going to do is DC fast charging, getting this DC electricity directly into a battery for a vehicle. That can be stationary batteries on site. That can go directly into the vehicle's battery as a DC-DC solution. And so recharging batteries with DC electricity is perfect for creating carbon offsets and reducing fuel use. The other one is blockchain. So here in BC, you can't connect a blockchain data center or mining rigs to the grid. You can't use hydropower for that application. So we're looking at off-grid volumetric solar and storage microgrids combined with wind power to charge batteries, and those batteries can run computing applications off-grid. There's a lot of talk about data centers and the amount of power that's needed, but you can imagine any data center can pop up volumetric solar and stack these units up to create the amount of energy needed. And all the data centers have UPSs already. A UPS has batteries, so you can charge your UPS batteries with high current from volumetric solar architecture. The other one is utility scale power plants. So being able to set up large utility scale power plants in the prairies and off-grid locations and do so really quickly. So we've got a 100 megawatt LOI signed there. And then we're working with a couple of mining exploration companies to offset their diesel emissions. So when they're exploring for resources in remote or off-grid locations, they can use volumetric solar with that battery microgrid to be their primary source of clean energy to run their camp and their equipment and charge vehicles, and then have the diesel backup for when the battery's low, or that they can use that when they need to. So the DCFC station, so one of the biggest misconceptions is that all solar energy needs to connect to the grid, and right now the grid is a bottleneck. It's a bottleneck, as I showed above, is that when you have so much solar energy in the middle of the day, the grid doesn't want it because then it reduces the price of other generating sources, and they still have to keep this reserve capacity to meet the high demand between 4 and 8 p.m. So where else can we send solar energy? We can send it directly to vehicles. So sending it to vehicles is worth about 10 times more revenue than selling it to the grid in a lot of places. So in BC, you can get 8 cents a kilowatt hour, but selling it to the grid, but you can also get 85 cents a kilowatt hour selling that solar energy into a car or a truck. So the next thing is to use volumetric solar forests with modular DC fast charging stations to create networks of vehicle chargers that are everywhere. So this is a couple of renderings of what that could look like for a 100 kilowatt peak system, volumetric solar architecture, 2 examples, one with a reflective base underneath, one without. And this has a volumetric solar 4x2 system. So each tower is 4x2. That means 8 bifacial modules. And we got a 5x5 grid, which gives us 25 total towers or trees. So in total, we've got 200 bifacial modules here. And then you just need to select the size, the wattage. So in this case, they're 500 watts. So 200 times 500 gives us our 100 kilowatt peak capacity. Again, we can boost that with more reflection, and we're running that from sunrise to sunset every day. So one of the plans that we have is to create a network in BC, and BC's got some great incentives for low carbon fuel credits that we can deploy these stations, especially in off-grid areas and underserved locations that maybe aren't on main highways. And we can work with other indigenous communities and commercial partners to get these systems deployed quickly. So you can use it for charging as a revenue generator, and you can also connect that energy into microgrid solutions for thermal heat and other applications that right now it takes a lot of time to even get a utility connection or make new power lines. In some cases, it takes years to get a utility connection in remote locations or new developments. The government is very supportive here in Canada and BC for solar and storage. There's federal incentives, tax credits, capital cost allowances. We've got low carbon fuel credits, so every kilowatt hour you put into a vehicle or you displace in diesel, you can generate additional credit revenue on top of the electricity and fuel savings. You've also got no PST, and then you've got a bunch of rebates from the utility, the power utility, because they want batteries too, so they don't have to, they want solar and storage too, so they don't have to buy expensive power during peak events from neighboring provinces or states. So the other thing is there's a bunch of accounting benefits that the capital expenditures can be, have investment tax credits and capital cost allowances, but it works out to a lot of rebates on this type of clean energy solution. So that's volumetric solar, a quick overview of the development, the next steps, the economic model. It's available today as an IP license for the architecture, and it's available on volumetric.solar website. There's a couple of renderings to show you from an architectural perspective, and this shows a charging station with a direct DC connector, and you can imagine that these would be anywhere that you could just drive up and plug in and charge your car or your scooter or your phone or whatever it is that you want to charge with solar energy. This is just a rooftop example. We can use volumetric solar vertically to add density to building power plants without having to deal with a lot of rooftop issues about rooftop membranes and leaks and snow clearing and all those things that are challenges in a lot of places. So to be able to stack these structures vertically, you'd need a structural engineer on board. We provide those third-party services to make sure this is well mounted. Again, the modules themselves are rated for hurricane force winds, so we're just adding more and more structural components as needed to ensure that we can stack these as high as they need to go. Ground mount's probably the fastest and easiest with the 4-post system. Quick to install. You can imagine getting these all shipped to site, prefabbed, all the correct lengths and modules in containers, and then being able to quickly clamp them together, deploy them, and create a power plant array, a very low footprint array that will work from dawn till dusk. And then you can add reflective surfaces if you want underneath, bounce some extra light up on the outsides and the insides. You can also add reflective surfaces around the structure, so you can put reflective sheets up. And if you think of this almost like a sail or like a fabric type system, you can put reflective materials up to generate an extra bounce of light. This is what it looks like if you were to look at it from the side. But now the amount of space this solar power plant would have taken up, both in terms of modules and mounting, civil works, all that stuff, we can create a high density volumetric solar installation that uses far less area and reflects that energy for an extra bounce. So you're paying for less modules and you're boosting them with reflected energy. And you can imagine the system on ships or other vehicles potentially, or even off planet somewhere in some sort of other locations. But anywhere the sun shines, you're going to have the ability to collect solar energy in 3D and add reflection to boost that power. Again, if you're wiring these in parallel first, you can stack up that amperage vertically and keep a nice low voltage. And then you can connect these towers together in series if you want to build up your voltage, or you just get those towers connected in parallel to battery systems, right? So batteries have low voltage, and they have the ability to accept higher currents. So the higher current charges batteries faster. So we actually want low voltage, high current battery systems, safer to install and charge your batteries faster. So that's a quick overview of volumetric solar architecture. It's available today. There's still work to be done on the DC fast charging networks, but I wanted to thank you for watching this video, and let me know if you have any questions or comments. Again, if you want a license to build your own, they're available on our website, volumetric.solar. Thanks.